All right, in this problem, we're going to have two blocks that are, one is on a plane, one is hanging over a massless, frictionless ideal pulley. And we're given the masses of the blocks, the static and kinetic coefficients of friction on the plane, and the angle of the plane. We need to find here, do the blocks move? So is block B, which is smaller, heavy enough to pull block A up the plane? If they do move, how fast? What is their acceleration? And then find the tension in the rope. So we'll label these do the blocks move. For that, we'll need to do the static check. How fast? We'll need to find acceleration. And then tension in the rope, we'll need to find T. So we'll follow the standard procedure for this of drawing the free body diagrams, assigning coordinate frames, writing equations for each block, and then solving those equations. So we'll start here with the free body diagrams. So for block A, we will have the weight of the block going down. We'll have the normal force from the plane. And then the weight of the block and the normal force, the angle between those is theta, same theta of the plane. And then we'll have the tension pulling that way. And then we will need to figure out which way the friction is pointing. So is A going to try to slide down the plane and have friction hold it up? Or is the tension going to pull A up the plane and have friction try to hold it down? We don't actually know which direction friction is pointing yet. So we'll have to figure that out. Now, for block B, we have the tension trying to pull it up, and then we have the weight trying to pull it down. And we'll assign our coordinate frames here. So we're going to assume that X is positive up the plane. So A is sliding up that way. We have Y, and then X follows the rope. So then in B, we have X going down, and we have Y perpendicular. This assumes that B is going to move down and A is going to move up the plane. So if we work it out and it turns out they do move, we'll be able to figure out which direction, and then we can adjust if we need to. But we'll just go ahead here and say that X goes down, Y goes to the side. And then on this one, we have X goes to the side, Y goes perpendicular. So how do we know which way the blocks are going to move? Basically, we know that since the rope is connecting these two blocks, so we have the rope, we have the tension in the rope connecting these two blocks, then we need to figure out if B is heavy enough to overcome the component of A's weight that is pulling down the plane, or if the weight of A that's pulling down the plane is bigger than the weight of B, then in that case, we would know that A would be trying to move down and B would be trying to move up. So this static check is going to have two parts. So for part one, we see which way the blocks try to move. So we'll compare weights of A and B in the X direction. So to do that, we'll have to calculate mass of A times G times whatever component of A is pointing along the plane. That's what component is in the X direction. That's going to be the sine of theta. Compare that to the component of B in the X direction, which is all of the weight of B. Mass of B times gravity. For A, we'll have 20 times 9.81 sine of 60 degrees. And we'll compare that to B, which is 15 times 9.81. put these into a calculator. We get 127.3 on this side, and we get 147 on this side. So mass of B, or weight of B pulling down, is greater than the component of A's weight along the plane. So B is heavy enough that A would try to move up and B would try to move down, which means that friction opposing that motion, friction is going to point down the plane. So now that we've compared the weights of A and B, the next thing on the static check is part 2, compare A plus friction to B. So in order to find that friction force, which that would be the static friction, to see if they move or not, then we need to actually write equations in X and Y directions. So let's go ahead and do that for each block. So for block A, we have sum of forces in Y equals 0 because A does not move off the plane. So we have the normal force going up. We have a component of the weight going into the plane, which that is the adjacent component, so the cosine, MA cos theta. So N equals, and that's times G, MA times G times cos theta equals 98.1 newtons. So now we can get the static friction. So static friction equals mu S times normal force, which is 0.7 times 98.1 equals 68.67 newtons is that static friction. So now we can go back over here where we were doing our static check, and we will basically just add in the friction force to this situation we've got going on up at the top. So we know that friction's gonna oppose the motion, friction's gonna help pull A down the plane, or prevent B from pulling A up the plane, really. So we'll have MA G sine theta plus static friction. Compare that to mass of B times gravity. And so we've got the 127.3 plus 68.7. Compare that to the 147. Well, we know that this is going to be about 195, really 196. So that's greater. So that means that the friction is too much for B to be able to pull A. Blocks do not move. So here the blocks do not move. And so we know that therefore acceleration equals 0, and tension in the rope is just going to be the weight of B. So that solves this version of the problem. Now, if we did want these to move, let's say, okay, so we know here that B is not strong enough to pull A up the plane with this much friction. Well, what if we just swapped A and B, and so that B was the heavier block and A was the lighter block? Then they would be a lot more likely to move. So let's switch those numbers around, and then we'll do the same calculation over again. So here we're going to say that A is the 15 kilogram block and B is a 20 kilogram block. So we know now for sure because we already did it before with them switched. Now that B is even heavier, we know for sure that B is going to try to move A up the plane. And so we can keep friction pointing this direction. Now we are going to need to erase some of these actual numbers. So our normal force will be different, and that will make our static friction different. And that will also make this stuff over here different. So now because B is heavier than A, we know automatically that B is going to try to pull A up the plane and B is going to try to sink down. So we don't necessarily need to compare these weights to see which direction the friction is going to point. So that's kind of lucky. We can just go ahead and erase all of that. Okay, so then doing that static check, now we only have one part to do, and that is to see if the blocks move or not. So we're going to need to figure out mass of A times gravity plus, times sine of theta, same as before, plus the static friction. Compare that to mass of B times gravity. So here we have 127.4 plus 51.5 equals 179. Okay, so now here, this 196 newtons from B is greater than the 179, so the blocks move. So yes, we'll write that here. Yes, the blocks move. So now to find acceleration, we need to go ahead and finish writing the equations now in the x direction for the blocks. So we'll have sum of the forces in x for block A is going to equal mass of A times acceleration. And so going up the plane, we have tension. And then going down the plane, we have the friction force, which in this case is dynamic friction. And we have that mass of A times G times sine theta. So we'll have 20 times A equals T minus 36.8 minus the MAG sine theta, which is the 127.4 we got up here. All right, and so that's going to equal also T minus T minus 164.2. So then for the blue block, we'll have sum of the forces in the x direction, which in this case is the vertical direction, equals mass of B times acceleration. And positive x is going down, so we have MBG going in the positive minus T going in the negative. And so this is really important to pay attention to which direction is x pointing. That way you make sure that you're putting your positive forces in the direction of positive x and your negative forces in the direction of negative x. Don't mix those up or you won't be able to get the right answer for acceleration or tension. Okay, so now we plug these numbers in and we'll have 20. Let's see. Oh, we messed up right back here. This is not a 20. Mass of A is now 15. So we'll just plug that in there. That's 15. And then back to B, we have 20 times A equals the 20 times the 9.81, which we had 196 right there. So 196 minus T. Okay. So now we need to take the blue block equation and the red block equation and combine those. So let's write them back up here. We have 15A equals T minus 164.2 from block A And then from block B, we have 20A equals 196 minus T. So if we combine those, you can solve this by substitution, where you rearrange and solve for T and plug back in, or you can solve by elimination, where you just add these equations together. And so if we do that elimination, we'll get 35A equals 196 minus 164.2. And so A equals 196 minus 164.2 divide by 35. We put that into a calculator, and A equals 0.914 meters per second squared. So now for T, we can solve either one of these equations for T. So we'll just go ahead and do this top one here. And we'll say that T equals 15A plus 164.2. We just move that 164.2 to the other side. So now T equals 15 times 0.914 plus 164.2. And finally, T equals 178 newtons. And this tension is less than the weight, and that makes sense because B is going down, so the tension is not able to hold B up. If tension were equal to the weight, then B would be hanging still. But instead, it's falling down, and therefore tension is less than the weight. So this is how you solve a 2 blocks problem when one block is on a plane with friction and one block is hanging.